The universe hides clouds that glow brighter than any sunrise, and they whisper the secrets of darkness itself. Stay with us, because the number one revelation is something almost nobody guesses, and you'll want to hear it before the countdown ends. Imagine a patch of the sky that is unexpectedly colder than its surroundings, a puzzling dip in the otherwise uniform afterglow of the Big Bang. The cold spot, spanning about 5 degrees, has sparked debates about whether it hints at a supervoid or even exotic physics beyond the standard model. Researchers using data from the Planck satellite and ground-based observatories have mapped its temperature anomaly, finding it roughly 70 microkelvin colder than average. While some argue it could be a statistical fluke, others suggest a massive underdensity of galaxies aligned with the line of sight, possibly a cosmic supervoid that stretches hundreds of millions of light-years. This feature challenges our understanding of large-scale structure formation and offers a rare window into the interplay between visible matter and the unseen dark components of the universe. Up next, we'll drift into the massive Fermi bubbles that stretch far above the galactic plane.
Floating high above the Milky Way's core, the Fermi bubbles are gigantic lobes of energetic particles that glow in gamma-ray light, extending nearly 25,000 light-years each way. Discovered by NASA's Fermi Gamma-Ray Space Telescope in 2010, these structures appear as sharp-edged, bubble-shaped emissions that rise perpendicularly from the galactic plane, hinting at a powerful, ancient outburst from our central supermassive black hole or a burst of star formation. Their uniform brightness and hard spectrum suggest particles were accelerated by shock waves, possibly from a past jet episode that injected energy into the halo. Estimates place their total energy output at around 10 to the power of 55 ergs, comparable to millions of supernovae, making them a key laboratory for studying feedback processes that regulate galaxy evolution. By tracing how these bubbles interact with surrounding gas, astronomers gain insight into how dark matter halos shape the distribution of baryonic matter. Next, we'll uncover the hidden darkness of Barnard 68, a dense cloud that swallows starlight.
Surprisingly, a seemingly empty patch of sky can conceal a massive, cold cloud that blocks the light of background stars, and Barnard 68 is exactly that. Located about 1,500 light-years away in the constellation Ophiuchus, this dark nebula spans roughly 2 light-years across and contains enough dust and gas to form a future star system. Infrared observations reveal its dense core, where temperatures dip to just 10 K, making it an ideal natural laboratory for studying the earliest stages of star formation. Its well-defined silhouette against the Milky Way star field allows astronomers to map its internal structure with remarkable precision, offering clues about how turbulence and magnetic fields influence the collapse of molecular clouds. By comparing its mass, estimated at a few hundred solar masses, to theoretical models, scientists refine estimates of how much of the galaxy's hidden mass resides in such cold, opaque regions. Coming up, we'll explore the Boötes Void, an enormous cosmic cavity that challenges our expectations of galaxy distribution.
Hidden deep within the tapestry of the cosmos lies an expanse almost entirely empty of galaxies, a region astronomers call the Boötes Void. Spanning roughly 330 million light-years across, this colossal void contains far fewer galaxies than statistical models predict, making it one of the largest known gaps in the large-scale structure of the universe. Its existence was first reported in the early 1980s, and subsequent surveys have confirmed its profound underdensity, suggesting that dark matter and dark energy may have orchestrated its formation by pulling matter away. Some simulations propose that such voids act as cosmic scaffolding, influencing the flow of galaxies along filaments that border them. While the void itself appears barren, the few galaxies that do reside within are often unusually bright or active, hinting at unique evolutionary pathways. Up next, we'll turn to the Perseus cluster's radio halo, a diffuse glow that maps the invisible magnetic fields threading a massive galaxy cluster.
Only the most energetic particle seas can generate a faint, sprawling glow that envelopes an entire galaxy cluster, and the Perseus cluster's radio halo is a perfect example. Detected at low radio frequencies, this diffuse emission stretches over several million light-years, tracing relativistic electrons spiraling within tangled magnetic fields that permeate the intracluster medium. The halo's brightness and spectral shape suggest ongoing turbulence, likely stirred by past mergers of smaller clusters, which re-accelerates particles and amplifies magnetic fields. By studying its polarization and spectral index, astronomers infer the strength and configuration of magnetic fields that are otherwise invisible, providing a window into how dark matter's gravitational pull shapes the hot gas and cosmic rays within the cluster. Moreover, the halo's existence supports theories that dark energy's repulsive effect influences large-scale structure evolution, subtly altering how clusters grow. Next, we'll map the Laniakea Supercluster, the massive cosmic neighborhood that binds our Milky Way.
Scientists redefined our galactic address in 2014, when they unveiled Laniakea, a sprawling supercluster that stitches together over 100,000 galaxies, including the Milky Way, into a single gravitational basin. The name, Hawaiian for immense heaven, reflects its sheer scale, roughly 500 million light-years across, encompassing the previously known Virgo supercluster as a substructure. By analyzing galaxy velocities and applying a technique called the velocity shear tensor, researchers mapped the flow of galaxies toward the Great Attractor, revealing the boundaries of Laniakea. This massive structure highlights how dark matter's invisible scaffolding directs the motion of luminous matter, shaping the cosmic web. Understanding Laniakea also refines measurements of the universe's expansion rate, as the supercluster's gravitational pull can bias local observations of dark energy. As we continue to chart these vast networks, we gain a clearer picture of the universe's hidden architecture. Coming up, we'll examine the Dark Energy Survey's supernovae, bright beacons that illuminate the accelerating cosmos.
Rare cosmic explosions serve as lighthouses that pierce the darkness, and the Dark Energy Survey, DES, captured thousands of supernovae to map the universe's accelerating expansion. By measuring the brightness and redshift of Type Ia supernovae, standardizable candles, DES refined constraints on dark energy's equation of state, suggesting it behaves like a cosmological constant but with subtle hints of evolution. The survey's deep, wide-field imaging over 8 years produced a catalog of distant supernovae, some over 10 billion light-years away, allowing astronomers to trace how the expansion rate changed over cosmic time. These data complement observations of the cosmic microwave background and baryon acoustic oscillations, together tightening the picture of dark energy's role in shaping the universe's fate. Moreover, the supernovae reveal the distribution of dark matter through gravitational lensing effects observed in the same fields. Up next, we'll delve into the ultra-diffuse galaxy Dragonfly 44, a ghostly system that challenges our notions of galaxy formation.
Deep within the Coma cluster drifts a faint, ghost-like galaxy that appears almost invisible, yet its mass tells a different story. Dragonfly 44, an ultra-diffuse galaxy discovered by the Dragonfly telephoto array, spans roughly the size of the Milky Way, but emits only a few % of its star's light. Spectroscopic studies indicate it is dominated by dark matter, with an estimated mass comparable to that of a typical spiral galaxy, despite its paucity of stars. This extreme mass-to-light ratio forces astronomers to reconsider how such diffuse systems retain enough dark matter to survive tidal forces within dense clusters. Some theories propose that feedback from early star formation expelled gas, leaving a dark matter halo bereft of stellar material. Others suggest a failed Milky Way that never ignited fully. Either way, Dragonfly 44 acts as a natural laboratory for probing dark matter's distribution on galactic scales. Next, we'll uncover the Ophiuchus Supervoid, a vast emptiness that may hold clues to the CMB cold spot.
Legendary in its sheer scale, the Ophiuchus Supervoid stretches across roughly 1.5 billion light-years, making it one of the largest known underdensities in the observable universe. Its location aligns closely with the enigmatic cold spot in the cosmic microwave background, prompting some researchers to propose that the supervoid's integrated Sachs-Wolf effect, where CMB photons lose energy passing through a low-density region, could partially explain the temperature dip. Mapping this supervoid required combining galaxy surveys from the two MASS and WISE catalogs, revealing a complex, layered structure rather than a simple empty sphere. While the supervoid alone cannot account for the full cold spot anomaly, its existence underscores how vast dark energy-driven expansions can carve out enormous cavities, influencing the CMB's subtle temperature fluctuations. Understanding these connections helps refine cosmological models that tie together dark matter, dark energy, and the universe's large-scale geometry. Finally, we arrive at the most iconic Cloud9 object, the cosmic microwave background itself. We've journeyed from chilly spots in the afterglow of the Big Bang to colossal voids that swallow galaxies, each Cloud9 object a subtle clue about the hidden scaffolding of our cosmos. These mysteries remind us that what we cannot see often shapes what we do. If you enjoyed this descent into the dark universe, hit the like button and subscribe so you don't miss the next mind-blowing list, fresh space wonders every week. Which of these 10 objects left you the biggest impression? Let me know in the comments below, I love hearing your thoughts. Thanks for watching, and keep looking up.